sometimes gets missed, and there was some comment about this at the beginning, is other aspects, things like service to the community and education. And Jerry spends as much time in service to the community as anybody I know on NSF panels, DOE, Basic Energy Science, the National Academy, and the commitment to education. I've been fortunate enough to know many of her students and postdocs. The mentoring job she does is phenomenal. I actually had one particular contact with her ability to educate people. Probably 25 years ago, she came and visited and stayed at our house. And my son, who was, maybe 10 then, turned out Jerry decided to teach him about sampling and statistics. So one morning, Jamie and I came downstairs, and there at the dining room table are two children, my son and Jerry, and there's a big bag of multicolored gummy worms, that thing, and they've been taken out of the bag and separated into piles of colors. And she was telling him, well, we've separated, we're going to find out which one tastes better. We go down and sample each one, and then we have to repeat that cycle to get the statistics. This is just what you want. Your kid to have 27 pounds of sugar first thing in the morning. And, that was her ability to educate him. He still remembers that. So she really does deserve this award for a variety of reasons. What I wanted to do today was make a little pitch about a hot button that I've got. And it has to do with issues about conducting research in both industry and academic. They're actually quite similar in the way they've been going, I think, because in both cases, whether it's the NSF, NIH, or your boss in industry, you're being asked to do more with fewer resources all the time. It's getting harder and harder. I don't think anybody in the audience would disagree that it's gotten easier to get grants. That's getting harder. In industry, that phrase of do more with less, I think anybody who's an industrial scientist has heard this, that the number of resources is going down. And we have to look a little bit more out of the box in trying to do the research in a different way. And it's been talked about before, but I think we're missing a boat in a big way in not involving more collaborations between industrial scientists and academic scientists. And I know there's huge roadblocks, the lawyers get involved, there's IP issues and all that sort of stuff. But it gets a little bit simpler when you start to talk about retired industrial chemists. That some of the issues aren't there, and it's an opportunity, I think, to enhance research groups almost free of charge. If you can find somebody in your area who had a career in industry and is a regional scientist and get them involved. And this is basically what's happened to me at the University of Delaware, and I'm taking examples from that. I retired in 2009. I already had a track record in history with John Raybolt, and we co-directed a group. And then I came to the University of Delaware, and what I've been able to do over the last 3 or 4 years is move out from just John, I mean, as good as he is, we're getting into a rut, and start collaborating with 2 other groups. So today I'm going to give you 3 vignettes of some of the work that I've been fortunate enough to do now, illustrating how this can work. And it's been tremendously rewarding for me. I mean, this is going to be an effort that sounds more like the stuff that I've been involved in historically, polymers, soft materials, spectroscopy. But I'm actually learning about solid state, hard materials, and it's been a joy for me. And one of the pluses in the groups that I'm involved with, Matt Doty and Josh Lyde, are young faculty, just got tenure here, both hard materials people. It's created an environment where 2 camps that are ordinarily quite far apart, the hard materials person who thinks in terms of valence band, conduction band, interband gap states, electron hole recombination, and the other person from the organic soft materials side thinks of, highest occupied orbitals, lowest unoccupied, and localized excitation. And in our discussions, we sort of meet in the middle. And it's an education for the students that the concepts may sound totally different, but we're actually talking about the same effect in 2 different groups. So I'm going to talk about these 3 projects. Sandy's going to keep an eye on me. If I don't get to the last one, he'll give me a yell and tell me that it's fine. Do you have a problem with me that I've got to be over here?
Oh, we won't get it on video,
Well, that's a plus if you just hear my voice. Okay, so the first thing I'm going to talk about involves some work with nanofiber mats. Many of you who have been listening to John and myself over the last 15 years know we're involved with electrospinning, producing very, very small diameter polymer fibers in a non-woven mat formation. Electrospinning has been characterized up until recently by people publishing papers saying, I managed to electrospin another polymer. I managed to spin 2,4-dimethyl chicken wire. Well, we've got to get beyond that. You electrospin these maps, but what are you going to use them for? How are they of value? And one of the things we thought about is, can it be used as a SURS substrate? Because it becomes a three-dimensional substrate. These non-woven mats basically are layers of fibers going down that have three-dimensional character. So if we can use those as a support for a SURS active material, we should get sensitivity enhancement compared to a planar SURS substrate. So that's what we were going for here. And what we wanted to do was find a way to coat nanoparticles, nanorods in this case, onto these polymeric fibers. Been done in the past, but it's usually been done using covalent chemistry. You've got gold particles, you find a way to create a thiol link and covalently bind to it. The problem with that is you have to come up with a completely different way of doing it if you change the nature of the polymer and the fiber. And we wanted to get around that. So we're going to use gold nanorods for our SURS active component that we're going to stick on these fibers. Why nanorods? Well, instead of nanospheres, if you go to nanorods, right, you've got that aspect ratio, which gives you a second tunable plasmon resonance so you can adjust the covalent chemistry. And the concept was to use electrostatic attraction rather than covalent binding. So if we could establish charges on the gold nanorods and opposite charges on the fibers, then just let it self-assemble, we're going to essentially stick it to it, and it becomes a universal approach independent of the nature of the polymer fiber you want. So depending on the solution that you may want to try to do SURS out of, you might change your polymer. You don't want a water-soluble polymer if you're doing water-based stuff. This is a possible way to do this. So how are we going to put these charges on? And we're going to end up putting the charges on by direct contact, and this is actually, I didn't even know she was talking about polyelectrolytes, but we're going to use polyelectrolytes here as a direct attachment to the gold nanoparticles. And we're going to use layer by layer deposition to fully coat the fibers. So the concept is you've got a polycation and a water polyanion solution for the layer by layer, and you expose the fibrous mat alternately to these two things, and you start to build up alternating charges, and you can totally coat the surface. And depending on which was your last dip, that's going to define the charge on the fibers. And we put an opposite charge on the gold nanoparticles, and then just stick them together. So this is what we're going to use. The polymer in the mesh is polycaprolactone. That's what we're electrospinning the fibers to produce this three-dimensional non-woven mesh. We're going to use these two electrolytes, basically a negative one and a positive one, to put down these alternating layers. So we're going to synthesize gold nanoparticles, gold nanorods. We're going to put a PSS layer right on that to put that charge for the PSS. Then the PCl, we're going to do layer by layer deposition until we get good surface coating, and we measured that by contact angle. And then we simply expose these two together and have the gold nanorods lock onto that surface, being electrostatically bound, and then do SURS. Okay, so these are the gold nanorods that she was able to synthesize. This is Wenchong Tang. Nice mode there near the 785 laser that we're going to use for the SURS. Pretty good uniformity of the gold nanorods themselves in terms of the seed-mediated growth. Those are fine, but now when we start to put the PSS on the gold nanorods, which actually have a surfactant on there, we can actually see that the PSX does get on there based on the infrared spectra in ATR of the gold nanorods to start with, where you see the C-tab, and that's a reference spectrum of PSS. When we actually expose the gold nanorods with the C-tab to the PSS, we can see the PSS bands pop up on this. So we've got it on there. So we basically coated that gold nanorod surface with the PSS with its negative charge. We're going to put the polyelectrolyte layer by layer with a positive, negative, onto the PCl, and we can see just from the XPS that we're getting both nitrogen and sulfur onto that system. And I'm not showing it here, but she actually showed with the sequential up to about 6 layers, you can see the contact angle asymptotically approach the fully coated value. So everything's on there. So we prepped the two different possibilities coming in here, the nanorods and the base. Then when we take the treated PCl fibers and stick them into the solution of the nanorods, and what she ended up doing was a little bit in reverse, is we recorded the UV, the near-IR visible spectrum of the gold nanorods as a function of time that the fibers have been dipped in there. So the fibers are essentially pulling gold nanorods out of this solution, and that's what drop in the intensity of the near IR spectrum of the gold nanorod solution as a function of exposure to the fibrous mesh. So we're getting no gold nanorods on there. You can see it fairly nicely in the SEM. That's the base fiber. Interesting thing, depending on PCL, how you spin it and whether the humidity is high or low. And in Delaware in the summer, the humidity is high. You get this pockmarked surface, but it fills up fairly nicely with the coating. So we've got a pretty uniform coating of these things onto the surface. The surge looks fine here. On this particular case, and it really hasn't been optimized. We're using 4-methyl purity as a surge marker here. And we can see the 4-methyl purity down to the sort of 10 to the minus 7 moment here, pulling it out of solution fairly well. So it seems to work fairly well. We get saturation at a concentration that's in pretty good agreement with the calculated surface area of the gold nanorods there. Reproducibility is surprisingly good. These were actually different electrospun mats, spun under the same conditions, exposed to a constant concentration, and it's not too bad in terms of a reproducible substrate. You can also tune that density based on the time that the fibrous mat is sitting in the gold nanorod solution. So depending on the concentration of what you're going to analyze eventually, you might choose to use different gold nanorod densities because that'll determine your saturation. You can also see that it's clearly going on by the change in color for the plasma absorption. And it makes a difference in the surge intensity depending on how long it was sitting in solution in the gold nanorod density. But nobody really has an interest in detecting 4-methyl purity. You know, that's not a common EPA contaminant or anything. We're looking for a way to extend this to actually make it an honest-to-God environmental analysis tool. And the approach we're taking is to stick a bridging molecule onto the gold nanorods. The bridging molecule will have its own surge spectrum. But if the bridging, we're going to measure the shift in the bands and the degree of that shift as a measure of the capture of a metal ion. And this was done basically with copper. So these are the spectra of the bridging molecule on the gold nanorods as a function of exposure to copper solutions, and you can see the bands are changing. We don't even really care what bands they are or why. That just gives us essentially an empirical approach to measure copper capture. And we're looking now, once we showed it with copper, the target from the point of view of the EPSCoR program, the environmental sensing, is lead and cadmium right now, looking for capture agents there. So that's the first project that was more sort of classical, but again, it got us into regions that we hadn't been into before, a little bit more polyelectrolytes and some of the surge work. And that has been published. Okay, shift gears now, and the language is going to change. And in fact, up until I started working with this stuff, you never would have caught me dead working with things that had more than 5 different elements in the composition, like bismuth, aluminum, gallium, arsenate. But I'm working with Matt Doty's group, and this is a new material that we think may have potential for terahertz generation and detection. You know, the terahertz gap, which those of us in the audience that are my age or more used to call the far infrared, and I'm not sure why they had to change the name. But it is this gap between the region where you can generate radiation with electronic devices versus photonic devices. It's right in that gap. And there certainly is the belief that terahertz is useful in a couple of regions, certainly for communication, medical imaging, security, some of the scanners. There's a fair amount of hype about it, but some of it's pretty real. I'll show an example in a minute. And if you have something which is called a terahertz switch, if it functions properly, can be used both as a generation of terahertz radiation, so it can be used as a source, and then you flip around the way you use it, can also be as a detector. And the source concept is, if you have something that has a gap in here between materials, put a potential across it, and with a pulse of light, if you can generate free carriers, electrons, what's going to happen? The electrons are going to start to move under the potential. Moving charge gives rise to radiation. And if you think about this as a pulsed generation of these carriers, where the carriers appear and then disappear, that time dependence, when you Fourier transform it, will give you the frequency range that it's actually radiating in. So if you change the lifetime of these carriers and make it short enough, you can get down into the terahertz range. Why do people think it's reasonable? These are just 2 examples. One is medical imaging. It turns out if you've got a fairly good contrast for this particular breast cancer patient with carcinoma, you get fairly good imaging with a terahertz that isolates that tumor out. Surprised me. I don't know, Max, do you believe that? And then the other one, which is sort of interesting, is tooth decay. It seems to be very good at showing contrast for cavities. And if you have a choice between sitting there with x-rays coming in at you versus terahertz, I think you're going to choose terahertz. So there is potential for application. That's why we're interested in it. So the material we're using is gallium arsenide, and with people had shown previously that erbium arsenide nanoinclusions, so essentially they're erbium arsenide quantum dots that are sitting in the gallium arsenide, form a center that can affect the lifetime of carriers in gallium arsenide. So if you just use straight gallium arsenide, hit it with a visible pulse that's at the band gap or above, you create electron hole pairs. Those electrons could accelerate under a potential and give you essentially radiation, but the lifetime is too long. In gallium arsenide, the recombination time for electron holes is way up on nanoseconds, and that doesn't get you to the terahertz region. But people found that if you put erbium arsenide nanoinclusions in there, the lifetime of the electron hole pair generated by excitation into the band gap of the gallium arsenide drops by 3 orders of magnitude, nanoseconds down to picoseconds. So if you switch that on and off, you've got a terahertz source. And this is, again, basically what's happening. There's the gallium arsenide. There's the band gap, inner band gap states of the erbium arsenide. So the way it's shortening the lifetime is without the erbium arsenide there, all you had was the recombination across the band gap. Once you put this in here, essentially the electrons can fall down into that deep gap state and have a much shorter lifetime. You can deplete this electron hole pair either by direct or by recombination in this mid-gap band gap state. So it's looking something like that. Our interest was actually in terbium arsenide because it's fine-tuning the electronic properties of this system, and terbium arsenide was a possibility of doing even better than erbium arsenide in this terahertz generation. So this is what we're dealing with, band gap of gallium arsenide. We have no idea at this point where the terbium arsenide state is. It hasn't been detected. We know it's there, but these things are extremely difficult to detect optically in absorption. And they're non-emissive, so you can't see them in emission. But they'll still act as a trap and a mechanism for depleting those electron hole pairs. So there's a bunch of reasons for trying to do this. What we want to be able to do is essentially make measurements to characterize how good the terbium arsenide is at changing that lifetime and understanding how that band gap state and where it is in here affects our ability to shorten the lifetime of the electron hole pairs in the gallium arsenide. We do this with a pump probe experiment that's an optical pump terahertz probe. So what we're doing is we're coming in with a regen that's producing kilohertz pulses that are 100 femtoseconds, maybe a little less in here, and splitting it. Part of it is going into a zinc telluride crystal, which generates terahertz. That's a terahertz generating crystal. So we've got a probe beam, the terahertz is going to come in. The pump beam, we put in delay stages, and the pump beam is coming in at 800 nanometers, which matches the band gap for gallium arsenide. So this is the thing that's going to generate our electron hole pairs in the gallium arsenide. This is the thing that's going to probe and tell us how long those electron hole pairs are around. Because as we do this, we pump it up. Now there's electrons, free electrons up in the conduction band. And the density of states is huge, so terahertz can be absorbed by this. There'll be states within that high density of state area that will absorb terahertz. So as you kick the pump on, the first thing you see is a big terahertz absorption. As the electron holes disappear, that's going to decay down. And eventually, when there are no electrons left up here, there'll be no terahertz absorption, because down in the ground state here, in the valence band, there's no states that you can excite with terahertz. Everything's full down there. So that's what we're going to measure. So again, now when we start to look at the specifics for this, there are a couple of possibilities. When we excite up into this band gap, there's one process, which we're going to call T2, which is direct de-excitation back to the ground state, which is what we would see without any intermediate band gap states. Then there's a T0 process, which is electrons dumping into that band gap state, and a T1 process, which is the electron hole recombination. So if we look at that decay time, we think think we should be able to fit it with 3 exponentials. And that's exactly what we found. When you try to fit this with 2 exponentials, you can't get the short light in there, but 3 exponentials fits fairly well. And the belief based on our understanding of the physics is that the shortest one, T0, is the drop into that inner band gap state. The next longest one is the deactivation of that through electron hole recombination. And the longest is the original gallium arsenide state. So now that we can measure these 3 processes, we can start to try to say something about how deep is that gap here. Is this way down or is it up tight? If it's up very tight up there, we would expect to see a temperature dependence of these time constants because that could be thermally populated. If it's down deeper, well bigger, larger energy than KT, and these are running at very low temperatures, then we won't see any temperature dependence on those 3 time constants for that process. And what we see is the temperature dependence of tau 0, which is the fast one. You know, error bars are huge, so there's no difference between these. We don't see a temperature dependence there. We don't see a temperature dependence on any of the taus, really that's statistically significant. So that tells us now, okay, we've got an inner band gap state there that's actually pretty big. It's a gap up there. Thermally, we don't have to worry about it. And you can also tell how efficient those 2 processes are. When you do that 3 exponential fit, right, you get 3 time constants, but you also get 3 prefactors. And the prefactors are proportional to the populations in those states. You can never measure absolute, but you can start to measure ratios of 2. A over B tells me, you know, how much is in that upper level gallium arsenide state versus the trap state. So you can start to look at those ratios of those, and again, the temperature dependence of the ratios showed no change as a function of temperature. So this allowed us to start to say that there really is no temperature dependence in the region that we look at on these processes. The next thing you worry about is pump fluence. And what pump fluence is how much you're putting into that pump state. And what it's going to start to tell us is, are any of these trap states saturable? Can we hit it with so much light that we get a whole lot of electron holes, we get a whole lot of relaxation into that trap state, and it fills up and eventually saturates, and then it's not a path that we can deactivate for. So it'll say basically the time constant should start to get longer as a function of pump fluence. And that is what happens in this one. Okay, the time constant for tau 2 is actually getting longer and longer and longer as a function of the power that we're pumping into it. Tau 2 was that relaxation from the gallium arsenide band gap. So what that's saying is that our trap state is saturated. It's a saturable trap state, and the solid state physicists tell me that that means that this particular nano-inclusion is not a metal, it's a semiconductor. Don't ask me why they say that. I'm still on the learning curve for some of the solid state physics. So basically what we're able to do here is to say that there's no temperature dependence on these low pump fluences. There is a pump fluence dependence showing that these trap states are saturable. It turns out that the rates are not good enough to be used for terahertz sources, but they can be used for terahertz detectors. And just as an interesting point, the way you do a terahertz detector, remember I said for a source, the pump generates charges, the charges move under applied potential and radiate at the time constants of the pulse. The way you do this as a detector, did you do that? Just cancel, I think. Don't install it. Okay. Instead of putting a potential across, you still come in with a pump, and to detect terahertz, the terahertz gets put on at the same time as the pump temporally. The terahertz provides the potential drop because it has an electric field associated with it. So essentially you detect terahertz by coming in with a pump, coming in with a thing that you're looking to see if there's any terahertz there, and if there is, you'll get conduction, you get charge, you get current. So it's basically a photocurrent measurement using the terahertz as the E field that polarizes and lets the charges migrate and move and measure a current. So it could be used for this. And that's now in PhysRep B. Again, Matt was the primary person. Laura is the student that we co-directed, did most of this data analysis. How are we doing on time, Sandy?
Yep.
material, and this is done with Joss Side, where they think we may have come up with a pretty neat composition of matter for a new conductive infrared transparent material. And the need for infrared transparent and near-infrared transparent materials runs all through different optoelectronic devices. You'd like to have stuff that you can use as a contact material which you can get light through it. And you'd like the light to either be visible near-infrared or even infrared. So what's currently used? Well, indium tin oxide is sort of the standard now in the industry to use for transparent conductive contact. It's got good conductivity. The sheet resistance is very low. It's the purple curve here. But its transmission stinks. I mean, if you really look at it. Yeah, you can use it down in the infrared, but it's lossy as all get out. You can go to something like carbon nanotubes. You get good transmission through a carbon nanotube structure, but look at the sheet resistance. It's starting to come up. If you look at something like nickel film, you can get good transparency through a nickel film, but it's got to be very, very, very thin. Okay? Very, very thin metal films have terrible conductivity because you don't have the cross section. You can cheat and go with something like a nickel mesh, where you're using essentially a porous structure with the wire mesh giving you your conductivity and the holes between the mesh giving you the transmission. But it's a problem down here because the transmission actually isn't very good. Once you get to the longer wavelengths, the holes in the mesh aren't big enough to let the light through because of diffraction. So, and then there's PDOT, which is another. So there's a need here for something that's got sheet resistance down here, but good transmission. Well, in some work the group had done on indium gallium bismuth arsenide silicon dope, they found an interesting effect when they started to look at the conductivity as a function of carrier concentration. As the carrier concentration, i.e. sort of the amount of silicon in there as a dopant, got up there above sort of 10 to the 19th per centimeter, boom, you're getting conductivities now. And I switched the scales instead of looking at resistance, we're looking at conductivity. Good conductivity of these things at high doping levels. And you can get high doping levels simply by the temperature that you treat the material at in the growth process. And they went out and measured infrared transmission on these things with this particular material on an indium phosphide substrate. Because these are not freestanding supported films. These are real thin. So it's an indium phosphide substrate. They came in and showed me these transmission curves. They're physicists, so they plot in wave length, not wave number, either that or EVs, which I think you're going to see later on too. But they said, look at this, we're getting 100% transmission through this at high carrier concentrations, or at medium carrier concentrations. And that sounded odd. And it turned out what they were doing was they were taking the indium phosphide with this thin material on it, measuring the spectrum, and then taking a pure indium phosphide substrate and measuring it and ratioing to that as its normalization. Well, the reason they're getting 100% is that it turns out this material has less reflection losses on the front surface than the indium phosphide. So they weren't essentially correctly accounting for front surface reflections. And we talked about how we're going to solve that. And, you know, again, this really came up when you started to look at some of these transmittance curves and looked at the reflectance curves in addition to it. They were trying to tell me that this particular one was 100% transmitting and the same sample was 35% reflecting. Well, that's 35% too many photons. You know, if it's 100% transmitting, it's got to be 0% reflecting. So we started to do work, again, extracting the real and imaginary parts and actually calculating these things up, and we got pretty good agreement that the transmission is really down around 80% for this 10 to the 18th. It falls off with some of these others, but you're still getting sort of 20% transmission here on these high doping levels which have good conductivity. And if you compare that now on the reflectance curve, you get pretty good agreement with reflectance plus transmittance summing up to unity, so all the photons have been counted for. So in terms of comparison to the material that's out there, we're down in this region now of good low resistance, reasonable transmission, and it looks pretty promising. So that's sort of where we are. Before congratulating Jerry on this, I want to give you a little background on her. Okay, she's been getting awards for a long time. Some of us don't realize exactly how long. This was the first award that she got, and she's already very good at accepting. You know, the check is in that little thing right there. And she's also shown leadership, and a lot of leadership now. But she started showing leadership early. unfortunately, it was cheerleadership. Yeah, look, well, that's the really disgusting thing, and she looks the same today. Jerry understood dressing for the job. The problem is that the dress never changed, right? Working in the lab is the same suit as fly fishing. Okay, but she came to understand that dignity is an important thing as you get on in this career. You're well recognized. You know, the governor's appointed you to the regents, and still you sometimes look like that. and finally, she has absolutely no problem engaging in serious banana wars. This was a banana fight in the backyard with the boys who are now, one's in graduate school and the others, the boys are now here, not tiny. So there's a human side to her too. Jerry, congratulations.
I'm going to kill my husband for giving me
He had nothing to do with it.